Well, good morning, everyone. Welcome to the video number 4. This is on data analysis. I'm Dr. Ratankar Rao, helping you out to learn more about data analysis. Right? Okay. Let me share my screen. So, in the first video, we looked at an introduction to data analysis. What is the weightage of data analysis in IBDP curriculum for the 2025 examination? And then we also looked at what are the different types of graphs that we have. We saw a line chart, we also saw a bar chart, and what is the each chart gives you and how is it useful in physics. We saw several examples of how to do graphical analysis in physics. And then what does each one of them reveal, or what is the physical interpretation? And this is what we have seen, and how appropriate scaling is important in case of graphs. And the next second video was on errors or uncertainties. What are the different types of errors? We saw about zero errors, parallax errors, random errors. We also saw about human errors, as you see in this case. And then we also seen about random and systematic errors. How do you identify them? What is desirable? And how do you account for them? Or if you have a lot number of random errors in any experiment, what is the purpose of having multiple trials, right? So in IA, this is very, very important to write. Okay, and then we looked at uncertainties. What is the minimum uncertainty? Okay, which one can have in an instrument? We have seen until here in your second video. Then we continued with the third video in handling uncertainties in calculations. So this is something which is very important for your paper 2 also, I told you in that video. So how do you handle uncertainties given a value like y is equal to so much? Okay, how do you find out what is the absolute uncertainty? What is the relative uncertainty? How do you find out the percentage uncertainty? We just saw some examples based on this. And finally, we got a few values also. This is very, very important because in your paper 1 and as well as in paper 2, you come across several problems related to this. So in fact, in paper 1 from 2025 curriculum, they have put 15 marks for both SL and HL based on this. Okay. And then we have seen, okay, so about different types of uncertainty calculations. I think we stopped here and in the next video, we looked at the third video, we looked at the significant figures. So what are significant figures? So how do you use them? And while you have a mathematical, okay, how do you infer the significant figures? And while you have a mathematical manipulation like addition of two numbers or real numbers or addition, subtraction. So how do you find out what is the end product, end value, how many significants you need to put it across? In several question papers, they have very clearly mentioned, okay, how do you put this put this into two significant figures, three significant figures, and so on. You need to know about this. Okay, and now what we look at into is graphical analysis, the mainstream part. Okay, so when you have a graph, most of your data analysis papers will initially start with a graph. Will start with an experiment. They'll give you a graph. Then they'll say maybe fit a what do you call a line of best fit, or maybe a curve of best fit. Then find out what is the uncertainty. Then do something like error analysis. All this will come into play. Okay, so let us do it one by one. Now, first one, see, whenever you talk about a graph, four important parameters are extremely important. The first one is slope. The second one is area. The third one is intercept. The fourth one is coordinate or pixel. Okay, let us see in detail how these four parameters provides us or sheds us some great information to us. The first one is slope. How do you find a slope? Slope is nothing but the difference in y values divided by difference in x values. Let me choose a different color of the pen because it's white. Okay, so therefore this is your difference in y values, this is your difference in x values. So you find the slope given by slope, or maybe I'll write here, slope is equal to difference in y values by difference in x values, right? Delta stands for the change in y values. So if, for example, in this case, difference in y value is something but the height, which is given by delta x. So you find out what is the height here, which is 2000 from here, and this is nothing but 525. So I'll write this as 2000 minus 525 divided by delta t. What is delta x here? Change in x values. Corresponding to this value, this should be around 6.4 here, 0.5 here, 6.4 minus 0.5, right? So I will get some value. So this values I'll represent it, okay, and this will be your slope. Now, in case of a straight line, you can take a slope either here, you can take a slope here, you can take a slope here, or you can take a slope here. You can take a slope at any point of any place. Okay. provided this is a straight line. If this was a curved path, don't do it. Right. Now, in case of a curved path, what will happen? You can take, if you take a slope here, then this slope would be different than this slope over here, right? Then, so as a result of it, the slope keeps on changing in case of a curved path. So you should be very careful. Depending upon the context of the problem, you need to decide where you want to take the slope. Okay. Now, let us move on to the next one. So when I just say context, it will not be clear now. Maybe when we start solving problems. Okay, I forgot to tell you. So from tomorrow onwards, we will be putting across problems, that is the homework portal problems, which will be exclusively only on data analysis. You can refer to those problems, and if you do not get the answer for it, you can come back to these videos, look into what is required, and then re-attempt it. Okay, still if you do not know, then in the evening, I will be posting across the solutions. Okay, next. Second one is area. So we have already seen slopes gives you some information. How does the value of y vary with the value of x? That's what it gives you. The second one is area. Area will give you something like one parameter. Let us say in case of a VT graph, which you already learned in your kinematics, area will give you the displacement of the particle. Will give you the displacement of the particle. If this was the speed, then speed versus time will give you the, sorry, here also you can find out the distance traveled by the particle. How do you find distance? If suppose this area is A1, this area is A2. See, definitely A2 would be negative. If I take A1 minus A2, this will give you a displacement. If I take A1 plus A2, though it is negative, I consider this as positive. Okay. In that case, I get the total distance of the distance traveled by the particle. Okay. So therefore, you can find out the area. Yeah. By finding out the area, you will be able to say what is the distance or the displacement traveled by a particle. Okay, so area is a very crucial measure, very important measure in the area of graphical analysis. Okay, next is intercept. Intercept is also very important. Okay, what does intercept tells you? Where does a given line cut the x-axis and y-axis? Many places you had not been using intercept so far, but it's very, very important. I just came across one problem, okay, which gives you the intercepts. Okay, as you see here, this straight line passes over here and stops over here. Okay, it cuts this. What does this cutting refer to? It gives you x naught equal to 400. What does it tell you? It means maybe the particle initially at time t equal to 0 is at this distance, right? So which means whenever we get this graph, what does it mean to us? It means that I have a timer with me. I start the timer and the particle is running from the origin, from me, okay, and I find out what is its velocity. But maybe the particle is not, maybe it is a running race. In the running race, the person whom I am going to click, so that person is already something like 400 meters away from me, right? And when I click it, okay, he is not nearby to me, he is not starting from the origin, he is already farther away from me. So that is what this tells you, okay? It gives you another parameter over here, right? So there was one interesting problem shown over here, okay, which says something like this. It says that Mr. Telson is holding his deadly three-point precision on the basketball court. For one of his shots, the height of the ball in feet as a function of the horizontal distance in feet, y of x is plotted below. So here what is being shown? The plot of y of x, that is the throw versus the distance where it falls has been shown. That is the basket where it has been thrown. Mr. Telson is standing at x equal to 0. He is standing at this point. What is the significance of the y-intercept of the function? What does this y-intercept represent? What does it represent? See, he is holding his ball in the hand and is throwing it like this, which means what? So this is the height of Mr. Telson, and then he is holding the ball over here. So this tells you what is the initial height of the ball, right? So though nothing is being given directly, but you can infer it here. In a similar way, what does this point tells you? This is the place where the basket is being held over here. This is the place where the basket is being held. You throw the ball over here, ball comes here, describes a trajectory, a parabolic trajectory, and falls into this. And this is nothing but the height of the basket from the ground. This is what is being shown over here. Or maybe after some time, what happens? The ball falls into the basket and immediately falls down like this. And if it falls down, okay, this is with respect to time, and you are able to time it up properly, then this slope will tell you, what does this slope tell you? Your height versus distance, height versus time over here, height versus time, which will tell you with what velocity it is now falling from here, right? Okay, now next point, pixel and coordinate. Okay, so far we have seen three parameters. The last part is what the coordinates. So as you see, for example, I have a straight line passing through the origin and I want to find out what is the velocity at a given instant of time. T equal to 1 second. What is its velocity? 4 meter per second. How do I know? Drop a vertical here. It intersects this point, okay, which is a coordinate. You find out the coordinate, and from this coordinate, you will be able to find out the velocity of the particle, instantaneous velocity. So using this method, what you can do? You can find out the instantaneous velocity, right? So thus, any complex problems can be easily solved using graphs, and the graphical method is been like this. You need to use all the four parameters, right? So line of best fit. Now let us understand what is line of best fit. Line of best fit is nothing but it refers to a line through a scatter plot of data points that best expresses the relationship between those points. So what you do is, see, when you have a scatter plot, what is a scatter plot? Scatter plot is nothing but you put some coordinates, right? X and Y coordinate for this point, X and Y for here, X and Y for here. You put it across. Now what you do is the red line that you get here is a best gradient. Now before that, how do you arrive at this best gradient? What you do is take the minimum of one of the uncertainties, and this is the least one, and take the maximum of this one. See, this is the max of this uncertainty, and this is the minimum of this. Draw a line over here. This line tells you it is a line of worst fit. Okay, this is your line of best fit. This is your line of worst fit. LOWF, I write it. Okay. Similarly, if I take this one, the lowermost here, you take up this uncertainty here and take up this uncertainty here and draw a line here. So this is another LOWF. This is another LOWF. Let me call this LOWF1. Let me call this LOWF2. I made a mistake here. This is LOWF1 and LOWF2. Okay, LOWF1 and LOWF2. Between them, there's a small region. See, this goes like this. This comes like this over here. In between them, there's a small region over here. Now make a line pass to the valley of this and intersecting these two lines. When it comes like this will be your line of best fit. Okay. If you want to find the gradient or do whatever you want, you have to find from here. So this is your line of best fit. Remember, your line of best fit should always pass through all the uncertainty bars, through the error bars. Okay, which means what? When I say it should pass between the error bars, which means what? It can either touch the error bars here, or it should ideally pass to the midpoint of the error bars. What is an error bar? This is your error bar, right? Midpoint will be somewhere over here. This is your actual point, the median, right? So therefore, it should actually touch this and proceed like this. So thus, the uncertainty in a gradient is calculated as LOWF1 minus LOWF2. What do you mean by LOWF1? Which means the gradient of LOWF1, which is taken here as M here and here as M here. Let me call this as M1. Let me call this as M2. So you will be writing this as M1 minus M2 divided by 2. Okay, so M1 minus M2. Uncertainty is M1 minus M2. So you'll be using this. And percentage uncertainty is nothing but this uncertainty, whatever you get over here, divided by the gradient of LOBF. What is LOBF? The line of the best fit. Okay. So in most of the papers that you see, the moment a graph is given, they will ask you to write down the LOBF. What is LOBF? So you have the error bars given like this. So you need to take the midpoints over here and as much as possible draw a smooth curve like this. Okay. See, when I say a line of best fit, it doesn't mean it should always be a straight line. Okay. Never draw a line like this. See, when I have, where is it? Okay. When I have, for example, here in this, for example, so it is a curve of best fit. See, so you have several points over here. Don't assume that all these points should be joined by a single line like this. Okay. Something like one straight line here, other straight line here, third straight line here, fourth straight line here. And it should not be a broken one like this. It should not be a broken one like this. It should not be a broken one like this. It should be a smooth curve over here. So this is the smooth curve that we expect over here. See, so most of the time it will pass through it. Okay, but sometimes it may not pass through 1 or 2 points. In that case, what you do is you assume or you imagine that it is very closer to most of the points. Okay, this is called as a curve of best fit. So usually they will not ask you curve of best fit. They will ask you about line of best fit. Line of best fit in this one is also a curve over here. Okay, when I say a line of best fit, it is not only a straight line. It could also be a curve. Okay, so this is your curve of best fit, which means A trend line that passes through most of the points is called as a line of best fit. Okay. Now, so we have seen the next part also. We will do the last video, which is on transformations. What are the different types of transformations we have, and so on, in the next video. Thank you. Be in touch with it. So see to it that you like the video, share, and subscribe, which would also help me and the YouTube algorithm to show such kinds of videos to you. Thank you.